Hello, everyone, and welcome to today's log reading group. Today we're having Sanjeev discussing his new paper, StABIE, about stability-aware training of neural network and interatomic potential. If you want to join this reading group more often, you can join yourself every Monday on the Zoom link given below, and you can press the subscribe button.
Hi, I'm Sanjeev. I'm a second-year PhD student at Berkeley, advised by Aditi Krishnapriyan. And really excited to be here. Thanks so much, Hans and Dominic, for having me. I've, as I said, been attending these reading groups for a couple of years now, and so I feel privileged to be able to be on the other end today and present a paper. So really looking forward to everyone's thoughts and input. This is a preprint right now, so definitely still is going to go through further development in the future. And yeah, very much looking forward to it. So real quick, would like to acknowledge my wonderful collaborators on this project, Ishan and Aditi at UC Berkeley, and then a collaborator at Google, Fabian Pedregosa, who is also integral to this work. So yeah, and by the way, so yeah, the title of this talk is Stability-Aware Training of Machine Learning Force Fields with Differentiable Boltzmann Estimators. So that seems like a bit of a mouthful, but throughout this talk, I'll try to unpack the various components of that and try to give a sense of the high-level motivation of this problem and what steps we took to solve it in this work. So we'll start with an introduction of this high-level space of molecular dynamics simulations, neural network potentials, and then this problem with stability that we attempted to solve or take a crack at in this work. So many of you here may be familiar with the general problem of sampling from energy landscapes. So atomic systems typically do not just exist in a single state, but exist in an ensemble of states, which are governed by their underlying energy landscape, right? So here you have something like a Boltzmann distribution, where at a constant temperature, the probability of a state is essentially exponentially less likely the higher its energy is. And so learning and sampling from this distribution is a foundational problem in science, in statistical mechanics specifically. And the applications are numerous, ranging from things like drug discovery, designing renewable energy systems, protein ligand docking, many problems. And so all of these, many of these can be thought to generally obey some sort of Boltzmann distribution from which it is desirable to sample. And the key component of this is learning the energy function that governs the system interactions such that you can sample from this Boltzmann distribution. And so a quick just recap of MD simulations. So this is a pretty ubiquitous way to actually sample from these high dimensional Boltzmann distributions. There are other ways to sample from Boltzmann distributions or just generally high dimensional atomic distributions. There's like Markov Monte Carlo sampling. These days, there's even ways to sample directly from the Boltzmann distribution with things like Frank Noe's Boltzmann generators work and things like that. But MD simulation is one tried and tested way to sample from Boltzmann distributions. And it enables us to simulate processes at atomic resolution, which is very nice. It gives us very fine level of spatial and temporal scale. And it also gives insight into the dynamics of your system, not just the distribution. And this is actually, I would venture to say, largely unsolved for proteins. We've kind of maybe solved protein structure prediction, arguably, with AlphaFold, but the dynamics of proteins are still, I think there's a lot of open problems there. And so we see some, examples of prominent MD simulations that have happened in recent years here. And so again, just to drive this home one more time, we can learn a lot from MD simulations across biology, material science, chemistry, et cetera. There's a lot of different properties and downstream applications which are unlocked through MD simulations. And this is just like a quick, just like a little picture of a coarse-grained MD simulation. This is actually, I think, generated by a neural network, but we'll get into how that works subsequently. So the idea of MD is actually very simple. Basically, it's just an integration with kind of like Newton's laws of motion. The key step is this step here where you're evaluating the energy of a state under some potential energy function. It was stated as U before, but in this picture it's V. And the idea is that you're essentially just doing like a gradient descent on this energy. So you estimate the energy, the potential energy of a configuration, and then you basically take the gradient of that potential energy and you march or evolve your system in the direction which locally minimizes that potential energy. And then you basically move your atoms in that direction according to some integration process. And you basically loop this for as long as you need in order to compute whatever quantities that you care about in the MD simulation, or until some event happens that you're looking, some rare event happens, or some computational budget is reached, perhaps. So this is really the simple bare bones skeleton of an MD simulation. And this boxed portion here, computing the U of R, the V of R, is by far the most important and non-obvious thing in the MD simulation. How do you actually construct this interaction potential? And so MD is expensive. Why is that? Long time scales. So a lot of scientific phenomena that we care about, things like protein folding or diffusion of ions in a membrane, something like that, occur on timescales that span maybe microseconds to milliseconds. So 10 to the minus 6 to 10 to the minus 3 seconds. However, MD simulations typically occur, or at least non-coarse grained MD simulations occur on time steps like 10 to the minus 15 in order to maintain numerical stability and some other considerations. So clearly this is a problem. We have a 9 order or 9 to 12 order magnitude, difference that we have to bridge here. And so you have to take, trillions or more steps to sort of actually iteratively sample or iteratively model the phenomena that you care about. The other thing is that at each step, if we want to accurately model the physics of a system, in theory, we need to do some sort of high fidelity computational calculation, specifically like a quantum mechanical calculation, or maybe an approximation like density functional theory, in order to obtain the energy. And so these are prohibitively slow for larger systems. So density functional theory scales as O of n cubed with the number of electrons in your system. And higher levels of quantum mechanical theory scale much, much worse, like O of n to the 7 or even O of n to the 10 for some coupled cluster methods. So essentially, yeah, go ahead, Hans. I see your hand is raised. Yeah. I think you're muted.
Thank you. How does the size of the time step differ between the different methods?
The size
like
of
the time steps that you can take in practice.
Yeah, that's a good question. I think so. Generally, I guess the intuition would be that larger systems require smaller time steps to maintain stability. I think in the land of like partial differential equations, they have like a criteria for this called like the CFL conditions, which tell you like the ratio between the spatial discretization and the temporal discretization that's appropriate for the system. I'm not sure in MD if they have a formal characterization of this, but I think the intuition is generally that larger systems require smaller time steps, which is why if you reduce the dimensionality of your system in some way, maybe via coarse graining, you can take larger steps, which is one of the appeals of that. Yeah.
Okay, but now if we talk about between the different methods, like if we have some DFT energy function or some quantum mechanical energy function or some classical energy function, there are difference in the size of steps that we can take.
It's an interesting question. I'm not sure about that. I would say that, I mean, yes, like a higher level of theory is more accurate. So maybe you can take a larger time step, but in practice, I don't think that is done. I think it's maybe more determined by the actual system itself, because if you have hundreds of atoms, and there's also an integrator that's evolving the positions, and so different integrators have different levels of convergence of how numerically accurate they are.
Yeah.
So I would maybe venture to say it's more a function of the integrator and the system than the force field that's used. But please, if someone knows better, please correct me if I'm wrong.
Maybe someone in the audience can enlighten us in the chat. All right,
yeah.
Let's continue. Yes, Johannes.
Hey, Johannes. Yeah.
I mean, hi. the frequency is usually the time scale is limited by the largest frequency you have in your system, right? And that's given by the atoms you have, right? So if you have a biological system, you have hydrogen atoms usually bound to a femtosecond or less. Then people do like shake or something and then freeze those out. But if you do like MD or solids where you have like, I don't know, only copper and very heavy, then you can do several femtoseconds over time scale because they move just way less in the same time, right?
So it's a
Okay,
function
but then
of
if we
system, yeah.
but then if we now care about, like if we do something like DFT, then I think we maybe care about some, I have no idea, right? But then maybe we also care about some electron positions or something like that, and they have even smaller time scales, and then we would need even smaller.
DFT doesn't give you electron positions, right?
Okay.
Because you just look at the electron density in total. If you really want to look at electron correlation, like real, then you need to go to attoseconds and whatnot. But then things get very complicated.
Yeah.
Is atto 10 to the minus 18?
That
Yes.
sounds right, yeah.
No. Okay. Okay, dokie. Thanks, Johannes.
Yeah, thanks. Yeah, and so right, so we've established that MD is expensive, and so neural network potentials are one, promising way that we've been able to kind of get at the expensive nature of MD in recent years. So the idea is to approximate this true energy function, which is maybe given by a quantum mechanical calculation, with a neural network that is learned via supervised learning. And so the general schematic here of how this works is that you collect some data set of a bunch of structures representative of your atomic system, along with their potential energy and force values calculated from either quantum mechanical calculation or DFT or some whatever you consider to be, whatever you can afford to run, and then you can consider to be ground truth for your system. You train a neural network interatomic potential, which is often something like a graph neural network or whatever, but basically some learnable function approximator. And then you train it to minimize this energy and force regression loss, such that it minimizes both the error from the true energy and the force in your ground truth data set. And the idea is that neural network potentials would scale much more gracefully with their system size than a DFT or quantum mechanical calculation. So like linear, quasi-linear for the neural network potential, as opposed to cubic or higher with these more first principles methods.
Okay.
And so
can we have a question from Lena?
Yeah.
Yeah, I have a question about this slide. So what is the typical size of the systems for which we can compute the energy and the force?
Do you mean the typical size that we can compute it? Like we can compute a ground truth like DFT or quantum mechanical energy function?
Yeah, exactly. Because I suppose we cannot do this for proteins because they're too big.
Yeah, that's true. So I'll preface this by saying I'm not a DFT expert at all, but yeah, you are correct in that things like proteins you can't compute. You can't really do like DFT for because there's just way too many atoms and too many electrons. So I think typically for protein force fields, people use things like amber or charm as like which are like, I believe, like classical force fields, but that have been very, very well tuned for proteins as the ground truth. And I think like if you're trying to do pretty higher levels of DFT theory, like more accurate versions of DFT, you quickly run into limits, like maybe no more than a couple hundred electrons or maybe a few thousand at best with DFT. Yeah.
Yeah, okay, but I think people then also do this or they train their neural network potentials on like small systems of DFT stuff, or like small systems of DFT simulations, and then they hope they can generalize to larger systems.
Correct. That is also true. Yeah. because again, the neural network scales linearly, so, or maybe quasi-linearly. So if you train on a smaller system and hope you can extrapolate to larger systems, that is a reasonable approach you can take.
Okay, thank you.
Yeah. So in recent years, many of you may be familiar with sort of the zoo of neural network interatomic potentials that have been developed that, there's been a lot of focus on architectures for these neural network potentials that have nice inductive biases and symmetries baked into them, things like invariance, equivariance to Euclidean transformations, like rotations, reflections, translations, etc. So there's been a lot of really, really cool work in this space. And I would say that we've now, it's still very much in development. There's still lots of architectures and innovations that are being proposed. But with some of these architectures, one could venture to say that on in-distribution tasks, so tasks in which the neural network is being queried on structures similar to its training data, the error in the neural network potentials, energies, and force calculations can often actually be much lower than even the DFT uncertainty itself. So this is like a table from the NNIP interatomic potential paper on this data set called MD17. And you can see in this last column here, these bolded numbers, these energy and these, force MAE values in milli-electron volts per angstrom. And so for people who are familiar with DFT, these numbers are actually like much lower than even DFT error relative to quantum mechanical truth in many cases. And so you're starting to sort of overfit to the DFT ground truth here. And so you can interpret that in multiple ways, but one way you can interpret that is that, okay, the neural network is doing pretty well, at least in modeling the ground truth data that it's given. So we have pretty expressive models right now, and they do well within their training data distribution. That would be like one takeaway that I would take from this. But the key point here is, these tables with lots of columns and like a bolded column at the end. This is something that in machine learning we're all too familiar with, because you need to have a table like this to submit to some conference. But I think the point that I'll talk about now is that we need to start moving beyond these kinds of metrics for neural network potentials. And the reason is that these metrics don't tell the entire story. The ultimate goal of an MD simulation is to recover, to model something interesting about your system. So to capture some observables about your system. So these are, system specific, but structural observables like the radial distribution function, dynamical observables like autocorrelation functions or diffusion coefficients, etc. And so this requires long and continuous simulation trajectories to fully sample the underlying potential energy landscape. And low force MAE, which is like how well do I do on this table here, doesn't necessarily correlate with stable simulation over long periods of time. And this is actually been really nicely shown by several recent benchmarking papers. One of my favorites is this one, Forces Are Not Enough, by Xiang Fu et al. From MIT, that came out about 1.5 years ago at this point. And they do a really nice job of illustrating this fact that you can have a learned potential energy that is very close to the ground truth. So that would give you very low, energy or force MAE. But just due to the nature of the errors, could actually produce very unstable simulations when you actually run a neural network potential in simulation. Because those metrics in this table, computing these metrics does not require running any simulations. It just requires querying the neural net on a set of static structures in your training data set, right? And so when you actually run simulations, you can see problems happening. Like you may match very, very well in certain regions, but just have local pathologies that cause you to completely explode or cause your trajectory to drift completely from the intended trajectory. And so we can see that a lot of state-of-the-art neural network potentials, despite achieving very good performance on these benchmark metrics, can actually sample some pretty highly unphysical configurations and basically be unstable, in the sense that, so this is an example from the aspirin molecule in the MD17 dataset. And so you can see some bond stretching events that occur that would never, or pretty much have virtually zero probability in the temperature at which this system was simulated. You would never really expect this to occur. So that's what we sort of denote as instability. And so this forces are not enough paper, among others, have sort of confirmed or at least hinted at this fact that if you rank a bunch of methods by their force MAE, that does not necessarily correlate with their stability or the recovery of important observables in the system. And so this is really the true motivation behind this work, that force MAE and these simplistic metrics are simply not enough to evaluate neural network potentials, and we need to actually run simulations with these models in order to ascertain how useful they are in practical applications. And so at this point, many of you may be thinking that thinking of this thing called active learning, which is something that was that's done to mitigate this problem. So active learning is this idea where you'd like to update your data set dynamically by collecting more data where the neural network is maybe inaccurate or uncertain. Maybe you use like an ensemble of predictors and you see where it's most uncertain, and then you collect more data in this region. And so this is a principled approach. It has certain guarantees. If you keep doing this, you'll eliminate the distribution shift between your that's causing this issue. But it does require querying like your original like DFT or quantum mechanical calculation method to obtain more labeled data. And so depending on the size of the system, this could be very slow. And so this is sort of a schematic of how this would work. And you have to call DFT here in this loop. And so this can be slow, but this is the way that the community has been approaching this problem by and large, as far as I am aware. And there's a host of works that try to do this in smart ways and stuff like that, but it can be very slow depending on the size of your system. So the guiding questions for our work essentially boil down to the following two things. Can we devise a training procedure for neural network potentials that explicitly accounts for the stability in when you run downstream MD simulations, and not just test set error on force prediction? And then number two, related to that, is can we do this in a self-contained manner that doesn't rely on any additional external labeled like DFT or quantum mechanical data? So these are our two sort of guiding questions that we hope to at least make a dent in this work. Okay, so I'll now go into the approach. Please let me know if there's any questions. Either drop them in the, so I'll take a look at the chat real quick. Oh, there is a question. Okay. Is the net force on the particle just du dx? Yeah, so the net force on a particle is actually the negative gradient, so that minus du dx. So the question is, what's the distinction between the loss terms on force matching and potential matching? Good question. So like you can think of it as like the function versus the derivative of the function. It's possible to match the value of a function without getting its derivative correctly. And it also, in practice, people have found that when you train to both energy and force, there's better properties, like better stability in training and downstream stability as well. So people typically train on some weighted sum of those two terms. The force term in the loss is typically weighted much higher than the energy term, but that is a hyperparameter that is system specific. Yeah. Great. All right. So we want to devise a training procedure that explicitly accounts for stability. So one way we might do that is think of training neural nets from a slightly different perspective. And that is what we call a top-down perspective. So what if we did the following? What if we ran an MD simulation with a neural network potential for some amount of time steps? Maybe we computed some empirical estimates, or like monoclonal estimate just means like an empirical average over your samples of some observables that we care about. And then maybe we could compare them to some known experimental quantities or some known values that you obtain from a high fidelity simulation. And then you could adjust your potential energy function according to some gradient-based, like gradient descent approach, and then repeat this. So this is another idea for how to train a neural network potential, and this is certainly not new. This has been done by several groups. There's actually some really great work from Rafa Gomez-Bovarelli's group here at MIT that has explored doing this kind of thing. And why would we want to maybe do this? The benefits of this, the most obvious one perhaps is that this introduces direct simulation feedback into the training process. So before we were just doing regression to energies and forces, and now we're actually running a simulation in the loop, obtaining some observable values, and then doing a gradient-based optimization with the simulation in the loop itself. So this is potentially helpful for the stability problem because you're actually running simulations during the training process, and you could perhaps correct instabilities that way during training itself. And it doesn't require any additional quantum mechanical or DFT data to do this. It does require this, experimental data or like data on your observables, but you can actually get that either from an experiment or even just by averaging over your true simulation, perhaps. So it's perhaps tractable to get this kind of quantity. I see a hand raised from Kriti. Would you like to ask your question?
Yes, Sanjeev. So one thing which I had in mind, like after you do the MD simulation right here, what kind of properties are you trying to get in target while doing the Monte Carlo? I was a little bit asking that.
You're asking what types of properties would I like to compute from the MD simulation?
Yeah, like after that step, like when you do the Monte Carlo step, the Monte Carlo estimates.
Yeah, so again, these examples I have here, radial distribution function and autocorrelation functions, these are just some examples I could think of. But this framework is general in principle to any observable that you could compute from MD simulation. So yeah, it's not really like you have to pick a certain one. In the systems that we looked at in this work, we were looking at things like the distribution function, autocorrelation functions, like diffusion coefficients, stuff like that. But you could apply this to things like stress tensors or whatever you wanted in principle, yeah.
Okay, thank you.
Yeah. Yeah, and so, we could imagine that this kind of approach might improve stability of our neural network potential, and also would satisfy the criteria of not requiring any additional quantum mechanical data. However, the significant challenges with this approach is that if you want to do gradient-based optimization through this MD trajectory, you need some way of obtaining gradients that you can use for stochastic gradient descent. And it's not entirely obvious how to do that from this approach here. And so there's been some work on figuring out how to do that efficiently. And so we'll discuss that. But that is a major challenge of this approach. And also, it's somewhat inherently ill-posed. So from like fundamental statistical mechanics, it is possible for two different neural network potentials with different parameters to produce the same observables if you only consider some sparse set of observables. So it's not a fully well-determined mapping where if you just give it one or two observables, it can definitively determine or constrain your potential to learning one specific potential. So that's also a problem we have to contend with here. So we'll tackle these one by one. The first is the gradient-based optimization. And so this involves a little bit of math. I will try to keep it at a high level to make sure that we gain the key takeaways from this. But so how do we actually do this optimization, right? So the idea is that we want to run an MD simulation, and then we want to compute some empirical averages of the observables. So let's introduce this notation here. So imagine that you have some Boltzmann distribution, which is basically parameterized by some Hamiltonian function that's learned by your neural network. And you're basically computing an expectation with respect to this distribution of some observable G. So essentially you run your MD simulation, which samples from a Boltzmann distribution, and you're computing some basically empirical estimate, some empirical average over some observable G. And we basically want to minimize some sort of loss function. So maybe like a mean squared error loss function where we, have this quantity and we want to minimize its difference from some reference value, G ref, which is maybe obtained via experiment or obtained via like a high fidelity quantum mechanical simulation or whatever it may be. So this is the formulation here. And so if we want to optimize this loss function such that the parameters theta of the neural network are changed to minimize this loss function, we need to use a stochastic gradient descent. I see a question that says, is a Monte Carlo estimate through many simulations or just one? Good question. You could do it through a single long simulation or many shorter simulations. That's called the ergodicity hypothesis. In this work, we do many finite length simulations to compute those estimates. And is there a specific reason for the Boltzmann distribution to be used? So in this work, we consider constant temperature MD simulations, which sample from the Boltzmann distribution. You could also have things like constant pressure or constant chemical potential or different types of ensembles, in which case the distribution would change, but they're all still exponential family distributions, which would still fit into the framework of this work. But we didn't consider other types of ensembles, but that's a good question. Yeah. Okay, so to optimize this via some SGD procedure, we basically need to compute the gradients of this loss function. So the gradients with respect to the model parameters. And we can expand this via a simple chain rule expansion. And really the tricky part is the second term. So this first term is just the gradient of the mean squared error, which is fairly trivial to compute in an auto differentiation engine. The second term is the hard one. So basically this is the gradient of the obtained empirical expectation of the observable with respect to the model parameters. So what is the sensitivity of the observable to the model parameters? And it is not obvious how you would compute this quantity. One option is to unroll and differentiate through the simulation. So you could unroll the steps of the simulator and consider each of those to be like some step in your computational graph. And you could then basically backpropagate through that using either like explicit backpropagation or use some sort of trick like the adjoint method, which was first described in this neural ordinary differential equations approach. And there have been a couple papers using this for molecular dynamics from Rafa Gomez-Morelli's group at MIT, as well as in other places. So this is certainly one option to obtain the gradients. The problem with this is that it can be prone to numerical instability and exploding gradients or vanishing gradients, especially if we're doing like hundreds of thousands of steps of MD. It's pretty hard, no matter what tricks you use, to get your gradients to stay stable throughout that whole process. You can do lots of fancy tricks, and a lot of them actually work pretty well, but at the end of the day, it can be a little bit difficult to get this to be stable. And so the other option is to realize that we actually know the underlying distribution that we're working with here. We know that there's a Boltzmann distribution, and this method here does not capitalize on that fact at all. So we know that we have a Boltzmann distribution, and the key intuition is that in an equilibrium or time-independent MD simulation, the individual steps of the MD simulation don't actually matter. They're just a way to sample an equilibrium distribution. And again, I will say again, this is for equilibrium molecular dynamics. If you're talking about non-equilibrium MD, then this does not work, but we're talking about equilibrium problems here. And so the idea is that we should be able to compute all the gradients that we care about only with IID or independently and identically distributed samples from our simulation. We don't have to actually track the path that was used to sample these states. We just need access to the samples themselves. And this is for some of you who may be familiar with this idea of implicit differentiation. This is an idea in machine learning where you can differentiate through optimization routines. This is essentially a probabilistic extension of that. So I'll quickly just mention this, that implicit differentiation is this way to differentiate through an iterative optimization routine without doing explicit backpropagation through that procedure. And again, the intuition is sort of analogous, that only the final solution matters, not the steps of the numerical optimization used to get there. So if I want to differentiate the solution to an optimization problem, the gradients that I obtain should not be dependent on whether I used SGD, a stochastic gradient descent, to get there, or if I used an atom optimizer, or if I used, I don't know, like some other, like Newton's method or something else, right? It should just be based on the fixed point that you finally reach. And so there's actually work from our group doing this to enforce optimization as a layer, to enforce hard constraints for solving partial differential equations and things like that. But the key takeaway is that basically we're looking at a probabilistic extension of this and realizing that we're converging to some sort of fixed Boltzmann distribution. And so it doesn't matter how we actually sample from it. We just care about the samples that we get from it. Yeah. And so to make this concrete, the estimator that we actually use is called a Boltzmann estimator. So this is the gradient that we care about obtaining. And the idea is that you can actually just estimate this with samples from the distribution. So this is very similar to this idea of like reinforce or policy gradients from reinforcement learning in machine learning. And essentially, you get an estimator that kind of looks like this, which is basically a covariance between the observable and the gradient of potential energies of individual states. So notice that there's no like unrolling through time here. It's just computing the energies of individual states and taking their gradients. And the intuition here is you want to decrease the energy of states that gave you low loss. So states that had that matched the observable well, you want to decrease their energy. So you want to increase their likelihood. And you want to increase the energy of states that have high loss, or you would like to decrease their likelihood, in other words. And if you do this in expectation, you should be able to decrease your loss function. And this was actually this is not the first time that this has been discovered. This estimator was also discovered by a work a couple of years ago, and they used sort of an entirely different approach based on thermodynamic perturbation theory to obtain a similar result. But we'll show some additional modifications we also made to this in this work to get it to work for our use case. But the key takeaway here is that we've somewhat, I'm hesitant to say we've solved the problem, but we basically have addressed the issue of gradient-based optimization through long trajectories, because we no longer have to explicitly backpropagate through a long unrolled simulation. We can just use independent samples from the simulation. So at this point, I would like to pause and see if there are any questions, because that was probably the densest part of the talk there.
Yeah, can you maybe go to the last slide?
Yeah.
So what we're doing now is we take our U, we roll it out a little bit, and then we have our trajectory, or we do many rollouts, and then you take the frames from each of the, like all frames from each of the trajectories. So do something like take the last frame from each of the trajectories and take this loss.
Yeah, good question. So if we want independent and identically distributed samples, in MD, each frame is correlated. So you need to do some sort of subsampling. So what we would typically do is we would run a bunch of simulations, and we would subsample at some frequency based on the decorrelation time of the system, such that you obtain uncorrelated samples. So maybe you take every 50 or every 100 time steps, and then you compute this estimator using those samples. Yeah.
Okay. And I mean, what you're doing in the end, you have this observable. Okay, so you could go ahead and from your whole trajectory, you calculate some no, that's what you're doing, right? This G of tau, no, what's the letter? Gamma?
Gamma.
This G of gamma is like, let's say it's the free energy that you now computed by the simulation that you ran with your neural network potential. Right? And now you multiply this computed value with the expectation of the gradients. Wow. So first of all, why is this Are we talking about a dot product here with these first two expectations?
Yes, this is well, this is like an outer product, right? So this would be this term, and then the second term is transposed. So
there's a trans.
Yeah.
Okay. And why is this a vector, like this this observable, this G of gamma?
Yeah, that's a good question. So if you think of like something like a radial distribution function, which I had a picture of somewhere. It's like there you go. It's like a histogram here, or it's a distribution over distances. And so it's a vector valued observable because it has a value for different values of R, for example. Or an autocorrelation function is a function of time. So you can, in a discretized fashion, represent it as a vector of subsampled values along this time axis.
Okay, so then what you're doing is you're multiplying all of your, now you basically have multiple observables, right?
Mm-hmm.
And we could also say that this is just one observable. That would also work, right? Correct me if I'm wrong. And then we would have and we multiply this one observable with our what is the gradient of the energy of the ensemble? So this is then just, we have many states, like all the states that you sampled from your rollouts, then you put those into your energy function, and then you now have many energy, many force values. So this is like a
I know these are not
matrix.
These are not forces. These are the force would be the gradient with respect to gamma. This with respect to theta, right? So that's different, yeah.
Okay, I have no intuition on this. What is going on here?
Essentially, so in the interest of time, I'll keep this high level, and I'd be happy to chat more about this. But essentially, this is basically a covariance between the observable and then the gradient with respect to theta of the observable. And so what this is with respect of the energy. So what this is saying is that you want to change your model parameters in a direction that empirically correlates with lower loss states. So in this case, it's just the G, which you then compose with the other gradient. But generally, the gradient the direction you want to go in is the direction that's correlated with lower loss values in general. Yeah. And so you're getting samples of that direction by computing this gradient on individual states. Yeah.
Wait, so this thing that we're looking at here, this you're saying is the gradient of this you're saying is the gradient or an approximation? No, it is the gradient.
Well, it's
that you write above here.
Yeah, it's a stochastic gradient because you're sampling some finite number of states to compute the gradient, so it's not like a but it's
we're writing an expectation here.
Yes.
Okay.
Yeah.
I'm somewhat fine. Let's look at the chat.
I see some questions. Okay, so how do you compute the reference observable? So in this work, we compute the reference observable by assuming that we have access to a ground truth data set of, let's say, DFT or of structures labeled with DFT. And we can just compute our observables by taking an empirical average over the data set. So if we want to compute a radial distribution function, we can take an empirical average over the data set, and then that would give us our reference observable. And then the next question was getting these IID samples. The timescales of physical correlations can reach into nanoseconds, which would correspond to much more than 50 to 100 steps of subsampling. That's a really good question that I don't really have a good answer for. I would say, in the systems that we considered, it actually didn't seem to matter that much that we had very uncorrelated samples, especially because stability is sort of a thing that kind of instability is something that happens very locally, like things just explode. And so like locally, if you have something that's totally getting messed up, you could probably capture that with just very local sampling around that region that's becoming unstable. But I would say yes, for more complicated systems, that could indeed be a problem. And yeah, okay. And then the question is, do we rerun the trajectory and resample periodically? Yes. So I will quickly describe how we actually use this estimator now, and that'll hopefully answer your question. Okay, I see we have about like 10 or 15 minutes left. I guess I will try to get through as much as possible, but then would also be happy to stay on longer and chat with people if people are interested. Okay. Yeah. Okay. So the other quick thing I wanted to mention is that the other challenge is that, you know, learning with observables is ill-posed because many observables or many neural network potentials can produce the same observables. The way we kind of address that problem is combining supervision from both the original quantum mechanical energies and forces with the observables. So we don't just throw out the energies and forces, we also jointly learn with them to constrain the problem to like a smaller manifold of possibilities, essentially. And so the way that our method works, so our method is called StABLE training or Stability-Aware Boltzmann Estimator training. Stability-aware because, well, it's designed to address stability, and then Boltzmann estimator because the estimator is the estimator that we use is the Boltzmann estimator that I described. And so the idea is to combine supervision from quantum mechanical energies and forces. So that's the typical, you know, training procedure that we use, along with these observables, specifically to improve the stability of these neural network potentials. So it's a multimodal training procedure because it's using these two distinct modalities of information to improve stability. So the first step is simply pre-training the potential in the traditional fashion. So you have some, let's say, assume access to a small data set or any size data set of energies and forces, and you do regression to match the energies and forces in that data set. And then once we have this pre-trained potential, the observable step is sort of, you can think of it as a fine-tuning step. So the idea is we now have this pre-trained potential and we actually start doing simulations. So we do a bunch of simulations until we find a bunch of simulations that have become unstable according to some criteria. Maybe the bonds have stretched catastrophically or something. And then once you've reached some threshold of, you know, maybe 80% or 75% of your replicas have become unstable, you start learning. So you freeze your simulation where you are, and you start actually learning with supervision from this ground truth observable. And then you keep doing this and resimulating from the point where it became unstable until you've reduced your instability below some threshold, at which point you then go back to simulation and explore more regions that have become unstable. And you essentially do this iteratively. So unpacking that a little bit more, you know, imagine you have a bunch of replicas you're running in parallel, and they each become unstable at different points. And you're checking periodically whether they become unstable. You find the regions where they become unstable, and you look at all the structures in the region immediately preceding the point where they became unstable. You pool all these together, and essentially this becomes the set of samples that you use to compute your Boltzmann estimator on. So you have your ground truth observable, you compute your Boltzmann estimator, update the model using stochastic gradient descent, and then you resimulate from the beginning of the window right before it became unstable. So that's the 0.3 here for this one. But then for these other ones, it's all different points. So it's like the beginning of this box essentially where right before they became unstable. So essentially you're always computing the gradients on these like near unstable structures that are gonna, within the next, let's say, a few hundred steps, become unstable. And then you essentially repeat this process until all or like most of your replicas have become stable and we're able to simulate from like 0.3 to 0.4 stably. And once we've been able to do that, we then resume simulating from 0.4, the place where we left off, and we just keep marching forward in time. So and we do this in parallel for like M replicas, so like around 100 or 200 replicas in parallel. We're doing this on GPUs, so it's pretty parallelizable, and you can have pretty high throughput with multiple replicas all at once. So this is the way this works. Yeah, I see a question from Lena.
Yeah, I'm just wondering, how do you make sure that this update is not going to increase the loss on the energy and the force? Yeah, do you keep updating this also, or do you just do it once at the beginning?
That's a really good question. Yeah, so I'll mention this at the end as well, but since you asked, basically, yeah, that's this point that we want to combine supervision from energies and forces and observable. So the idea is that we don't only take a gradient on the energy, on the observable loss, but we also are always including a term that's just regularizing it with the energies and forces on the original data set. So you always have like a term in your loss function that's continually optimizing that energy and force loss function to control for this fact that you might increase your energies and forces loss too much if you just don't do that. Does that make sense?
Yeah, it makes sense. Thank you.
Yeah. Okay, I see a question. What if after retraining replicas avoid the difficult region? That's an interesting question. So you're saying we just avoid the region where things became unstable. I guess if you did that, you would not capture your observables correctly, because if those difficult regions are important in the observables that you're calculating, I guess that would show up in your downstream evaluation. So that is something you can measure if that's happening. Yeah. Okay, so we have this method, and so I want to just briefly, since time is running out, so for people who have to leave right at the end of the hour, I would like to just give a sort of a high-level overview of what this enables. So how we evaluate this method is we say, how long can our neural network potential simulate without catastrophic instability? So after we've fine-tuned it with this training procedure, how long can it simulate stably? And then also accuracy. So considering the stable parts of the simulation, how closely do the estimates of the observables match the true values, essentially? So we're evaluating on these two axes. And so we're looking at these models and data sets. I can go into essentially this procedure is agnostic to the actual architecture you use. So we chose 3 different architectures that sort of are representative of different types of symmetries and levels of symmetry and levels of expressivity. And we also looked at a few just representative systems on a few different length scales. And so we started with this aspirin simulation from the MD17 dataset. And so the workflow here is you pre-train on 1,000 labeled structures, and then you fine-tune with the StABLE training procedure. And the observable that we're using here is the distribution of interatomic distances, which is a low-dimensional descriptor of structure that's kind of similar to a radial distribution function. And so you get some funky-looking loss curves with this approach. It's not just like a nice decreasing loss function. So what happens is that as we simulate, the fraction of unstable replicas here first starts to increase. So we're exploring more and more regions. We're exploring regions that are unstable, and we encounter more and more unstable replicas. And then we start learning with the Boltzmann estimator and decrease the fraction of unstable replicas. And then once we've decreased below some threshold, we repeat this, and we kind of just do this iteratively until we reach some computational budget. And so some things to notice here is that the fraction of unstable replicas goes down when we start learning. So this is like a basic sanity check that optimizing to these observables is helping with stability. And you're also seeing that the slope of how quickly things become unstable seems to be getting like shallower and shallower as you go, which means that maybe this is actually working. Maybe we're starting to converge on a potential which is more stable, or which becomes unstable slower, at least. And so you can see during a learning phase, our structures become, start at very unstable configurations with a lot of bond stretching and become more and more stable over time. And so we can actually see that when we evaluate on some downstream simulations, our models are actually a lot more stable than models that were only trained with the quantum mechanical training, even on models that were trained on like 50 times as much data. So a model trained on 50,000 energies and forces structures versus a model trained on 1,000 energy and force structures plus our StABLE training procedure are actually still considerably more stable. And we also see less noisy recovery of things like observables because we have longer sampling, and so we have less sampling error in the calculation of our observables. So we see better recovery there as well. And we also see, if we try to generalize to different temperatures, so we trained at 500 Kelvin, but if we want to try to evaluate how it does at different temperatures like 350 or 700, we see that in both cases, the model trained with StABLE training is considerably more stable, but also generally captures the observables more accurately than the method that was only trained on the energies and forces. So I see a quick question is, do you think your method is correcting the holes in the landscape or smoothing the landscape? That's a good question. We have tried to investigate this, like looking at the smoothness of energy functions and stuff. It's always a little tricky to decipher this. But yeah, my hypothesis is that it's sort of smoothing the energy function and like getting rid of these like very spurious spikes in the energy function, which may be causing instabilities. So I know it's almost the hour, so hopefully, I mean, I'd be happy to stay on for longer and chat. Hans, I don't know what if that's okay to stay on and keep chatting.
Absolutely, we don't have any time constraints.
Okay, cool. So I see a question. How might this approach compare with adversarial training, intentionally generating configurations with high uncertainty and training on them? This is pretty similar to that. You can think of the adversarial component as like we're seeking out these unstable regions. Where is that picture? Yeah, I guess so. You're simulating until you reach these unstable regions. So that can be thought of as an adversarial process where you're trying to seek out unstable regions. But then training on them, typically, I think maybe what you're suggesting is then compute the ground truth energy function on those configurations and then retrain on those. So that's the thing that we're not doing here. We're not querying a DFT calculation or something like that. We're simply relying on the signal from the observable for the training procedure. So that's the difference, is that we're not computing the ground truth energy function. But yes, you can think of this as adversarial training. Yeah. Okay. Right. Yeah, so we see some of these results here. We see similar results for an equip simulation of another system here, where again, we see improved stability, much better recovery of the observable, just due to the fact that we're able to simulate for longer, so we can get more samples and reduce our sampling error. And we see a general progression from sort of unstable to stable structures during the optimization process. One point I want to make is that there are some systems for which instabilities can actually arise in like very localized regions of our simulation box, meaning that it's not like a simulation, an instability that just blows up the entire simulation, but rather it arises in a very small region. So for example, you might have like a bond stretch here, an unphysical bond stretch in this water system that appears very locally at first, but then eventually would cascade to the rest of the system. And so the question is, can we like, so yeah, this is something that happens, for example, in a liquid water simulation when you use a GEMNet model. This is something that we noticed. And so the estimator that we currently have uses global energy and observable estimates, meaning that all of these quantities are computed on the entire system. Whereas if something is happening in like a very local subsystem or sub-region of your system, it's hard to see how this optimization process could actually guide you to fix this particular instability. The intuition is you want to decrease the energy or increase the energy of high loss states. But if you tell your model to increase the energy of this state, how does it know whether it's this atom over here or this atom over here? So there's no like localized information. And so we need a way to do some sort of localization here. And so the one idea is that we can actually compute local energies and observables by capitalizing on the fact that neural network potentials predict an energy for every atom and then sum over all the atoms to get your final energy. This is typically how neural network potentials are parameterized. And so we can actually just replace these global energy values here with just the energies of like subsets of atoms, essentially. And we basically say now, I want to sample like these local almost like solvation shells and compute this estimator on those quantities. So you can imagine that the energy of some local state, which is like a lowercase gamma here, is going to be the sum of basically energy of the individual constituent atoms in that local neighborhood. And so this is a sort of a simple but powerful modification we can make to this framework to be able to adjust or account for these local instabilities. So this is the original estimator, and essentially just replace these uppercase gammas with these lowercase gammas, which are just local sort of regions, these local little like neighborhoods, and compute the estimator over those. And we find that that actually makes a big difference. So I see a couple questions here. When you compare to QM training, does that include some form of training on your observable, or is that only energy and force matching? So the QM training means only energy and force training, so no observable involved at all. Do you see this approach being implemented with active learning? Yeah, so this approach is not mutually exclusive with active learning. I think you could do active learning along with this approach, and that would totally work. I haven't thought about the specific details, but I don't see any reason why you couldn't do both. How do you define instability? So instability is defined differently for different systems. For like systems like this water system, it's basically like a collision metric where it's like if two molecules are colliding or the bond is stretching too much or something, we have some heuristics to denote instability. Many of them we took from That Forces Are Not Enough paper, which is an excellent sort of, I would say, reference on instability in MD simulations. Do you only differentiate through the local part? So your neural network does not get information about the whole system. In this case, in the localized Boltzmann estimator situation here, where I just described this, yes, here you're only looking at local little regions of the system. So your model does not get information about the whole system. But then in the previous cases, you're looking at the entire system, or at least you're looking at the observable of the entire system. So some low dimensional representation of the entire system. Okay, I will keep going just in the interest of time and try to get to the rest of the questions as I go. So for this water system, we consider this observable, which is the equilibrium hydrogen-oxygen bond length. So this is the observable that we actually use for training, with the motivation being that, often we see these like crazy stretches that happen, and we want to try to prevent those from happening. And so similarly, again, we see that we're able to be more stable with the StABLE training process as opposed to without it. So you see, that the fraction of unstable replicas grows more slowly. So you're able to simulate for longer with this StABLE training process. And we're also able to recover these observables, this radial distribution function, much better. And really interestingly, in the short range of this radial distribution function, you can see like a bunch of collisions that are happening in the original neural network potential. This means that a bunch of molecules are colliding with each other in an unphysical way. But after our training process, we see that these collisions are greatly reduced, and that essentially we're able to prevent these collisions from happening after our training process. And we're also able to see that some transport properties are better recovered. So the diffusivity coefficient, which is something that is a function of longer trajectories, longer time trajectories. We see that because our potential is able to simulate for longer, you get basically smoother estimates of the diffusion coefficient than if you were to not do the StABLE training process, essentially. Okay, I see I'll try to address a couple more questions in the chat. Are there specific types of molecular systems or conditions under which StABLE training might not be as effective? That's a good question. I think in the current iteration of things, maybe systems that have like lots of different metastable states might be challenging at the moment, just because like the observable of any given state is necessarily only like maybe one local minima of your system, but there could be many. And so like, how do you actually know what local minima to enforce the observable under? That could be a problem. So maybe systems with lots of metastable states. The loss you compute is only a proxy for stability because it only measures one set of observables. That is indeed true. We would like to compute, in theory, we need to compute like a ton of different observables. You can just add those to your loss function and compute those the same way. So in principle, there's no problem with doing that, with computing multiple observables. But it just adds maybe computational overhead and cost, and like also manual tuning of like, okay, what observables should I use? But in principle, you could use multiple observables and sort of constrain the problem further. Okay, so wrapping up here, I think the key takeaways here is that for this training procedure, we're able to get more stable, more accurate, and more generalizable neural network potentials for the systems that we considered. We still need to do, I think, more validation to see how this works on other systems. And the key takeaway here is that we didn't use additional training data. So we didn't use extra DFT calculations to do this. We were actually able to just squeeze out all these results only on the existing data that we had, which indicates that the existing data actually has more exploitable signal than we were previously using. So existing data sets that have energy and force labels, there's this hidden source of supervision, which is the observable that you can just average over the states and compute it from your data set. And no one's really been using that before, but it seems like using that actually squeezes more out of the data sets that we have, and gives us more mileage for the data sets that we have. So this maybe points to the fact that we're leaving something on the table by only training on energies and forces, and that there's additional sources of information lurking in our data that we can use. And the procedure in principle is agnostic to the neural network potential architecture that you use, the molecular system you use, and also the sampling scheme. So this doesn't even have to be molecular dynamics. You could do basically any approach that gives you IID samples from your distribution, you can apply this framework on. So it doesn't even have to be molecular dynamics. A question on the underlying neural networks. What is an improvement in speed of simulations versus vanilla MD? Okay, you're saying just how much faster is a neural network potential than like a ab-initio molecular dynamics simulation? Yeah, so again, depends on like the level of theory that you're using for the MD simulation, but I've heard numbers thrown around. Like I've actually never done ab-initio MD myself, but like anywhere from like, depends on the system size, but for larger systems, it can be like thousands, tens of thousands, or even millions of times faster, depending on how big the system is. But yeah, it's at least a few orders of magnitude faster. Yeah. One parallel I'd like to draw to, yeah, go ahead.
No, I would just have gotten to the questions of the people with raised hands, but go ahead.
Oh, yeah. Oh, okay, yeah. Sorry, I didn't see the people with the raised hands. I was just looking at the chat. Yes, feel free to ask your questions. Go ahead.
Yeah, hello. Thanks a lot for the talk so far. It's been really nice to see like all the work you've done. One question, like all the examples that you show with instability show like very stretched bonds. In practice, did you observe any other kind of instability, like collision between atoms, angles getting like weird, or was stretched bond the main cause?
Yeah, so admittedly, we considered a limited set of systems, and I would say stretched bonds were one of the most prevalent failure modes that we saw. But we also, in these water systems here, sometimes we saw like, just two molecules that ended up right on top of each other, or like occupying pretty much the same space, which is obviously highly unphysical. So we also saw that happening. And then also in the bond stretching cases, like with the small molecules, sometimes we also saw bonds that like constricted too much. So we see a variety of different failure modes, but the bond stretching is the most dramatic to show in figures, so I tended to show those more.
Yeah.
Yeah.
That's why I asked the question, because like, is it just because it makes nicer figures or not? So if bond stretching, contracting, and atom collision are the biggest causes of like instability, wouldn't it be easier to directly tackle these? Like, I know why does it happen that there's instability there? It's because in the training set, all of the molecules are like somewhat low energy molecules, even if they're generated through MD simulation, right? They're still generated through physically like physical simulation that makes sense in some ways. And there would be probably ways of directly hacking the loss function to make it such that bond stretching and collision dramatically increase the energy. Instead of like having to run entire simulation to detect the instabilities and back propagating it. Like, or what about like just generating these unstable systems directly without running the MD, just like say, okay, well, at that point, I will just, I have this system, let me just move that molecule so that it collides with the other and say that this is an unstable system. Like, do we actually need to run the simulation? Of course, running the simulation will probably have a higher likelihood of detecting the actual failure mode of the system rather than any random possible failure mode that might never occur. But it also comes with a cost that needs to be done during the training. So why not try to correct these errors directly during the initial training?
Yeah, that's a good question. I think that's something that has been done before, like with active learning procedures, where you're kind of, I mean, that's kind of getting at that, right? Where you try to find like these higher, or you supplement the training data set with these high energy or very high, like very off equilibrium type of structures, and you try to correct for that directly. I think for these kind of small systems where the failure modes are somewhat predictable, that makes sense for sure. But I think there's also like so I would agree with you that that's a good approach to use. I think for maybe larger systems or just more complicated systems where it's maybe unclear how things are actually going to become unstable, or if there's more subtle instabilities that occur, this approach is like the approach that we've outlined is also beneficial because you're actually still getting direct simulation feedback. So no matter how much you add to your training data, there's still going to be some distribution shift when you actually simulate. And so the approach here is to try to tackle that distribution shift. But I fully agree with you that there are other ways to tackle this. I mean, another thing you could just think of is like adding a prior or something that just like penalizes bond length deviations, like a classical force field term or something like that. But then it's hard to know for all systems, like you have to add a bunch of terms. So it's like a bit of a manual process. So trying to avoid that.
I mean, like many of these things could, like there's maybe noising, denoising, using MD, and whenever the force in MD is too high, we penalize the network. Like there's many things that like we could try, but I do agree like with your approach. The thing that is very, very nice is that yes, you can try to tackle most basic like instability, but there are always like instabilities that you will not be thinking about that are like very much different of what you would think. And of course, this approach is really, really good to see. Having another question, like on a few slides back, when you show like that the number of epochs on the x-axis and the number of instabilities. This one. One thing I noticed is like here, like there's an increasing slope in like the number of stable replicas. So I'm not sure like whether your model is helping or like, well, can you explain that a bit?
It's a good observation. So I guess the way I would maybe interpret that is that, so this is during training, by the way, not during inference. So I guess the way I would interpret that maybe is that the model is like focusing more on the trajectories which are really hard to correct the instability on for whatever reason. And I'm not super sure. I haven't actually investigated specifically why this thing is going up. And I don't think this is actually like a common thing across all systems, but yeah, that's maybe one interpretation or explanation I could, like post hoc explanation I could have for that, is that essentially the model is like focusing, the training process is focusing on regions that are harder and harder to optimize well. Yeah.
Okay, so you still observe that on inference, it's better the more epoch you add, like, and the more number of simulation steps you do.
So the more epochs you add, I didn't show that result here, but like, yeah, you could take the checkpoints from like different epochs and show how the stability ends up at the end of it, like how this histogram, for example, ends up. And generally, like the longer you train, the more and more stable you get. But then you also start sacrificing things like you might really start overfitting, and your energy and force error of your potential might creep up, which depending on what kind of things you care about, you can tolerate a pretty high force, but if you only care about simulations, but that's something you have to be careful about.
Cool. Also, do you think like, because again, many of these instabilities happen at the local region, like bonds or angles or collisions, like, do you think that having like the fact that the energy is like a global value of the system and not a local value, do you think that like having local variables, maybe like the charge density, like the density of the charges at that point, or like I'm not sure exactly what other local variables we can have, but like these local variables, do you think they would help stabilize the system instead of just having like energy?
You mean as sources of supervision during the training process?
Yes, exactly. Well, I guess the forces are also local, right? The force on each
the forces are the local source of information. Yeah, so I would say we already do have local supervision, but I'm not sure. Again, as like a not really like a domain person, as a DFT person, like I don't know for sure how hard it is or easy to get those kinds of quantities from simulations, but I'm sure more information can't hurt for sure. But this localized information this is something that we were getting at with this whole localized Boltzmann estimator, the idea that you can kind of hone in on specific regions. That's one thing that we were motivated by.
Yeah, cool. Thank you.
Yeah, absolutely. I want to just quickly mention a couple more points before answering the last few questions that I see. So one kind of like way of thinking about this is a parallel to like large language models. So many of you might be aware that large language models are first trained via next token prediction on like a ridiculous amount of data, and then they're fine-tuned with this reinforcement learning with human feedback sort of approach, where they try to like filter out content that's like offensive, or like also just like stuff that's not actually answering the prompt that the user asked and stuff like that. You can kind of very loosely think of this as a similar approach, where we first train with energy and force prediction as like a pre-training strategy. And then, as I mentioned, that our method has connections to reinforcement learning and policy gradients and stuff. And you can kind of think of this as like reinforcement learning with observable feedback as a way to sort of fine-tune a neural network potential. So that's also like one more perspective I just thought was interesting to throw out there. Yeah. And so I think these other points are sort of a bit more subtle. So I'd be happy to go into them. But the final takeaway is that another takeaway is that we currently can't use this method for dynamical observables. So observables which are path dependent are not super compatible with this approach, because we would need to optimize over paths. And so we cannot use IID samples anymore. So that sort of breaks this a little bit. There are ways to get around this, but they're kind of complicated. So I didn't include them in this iteration of the work. But yeah, really the next steps are to integrate this into the community workflows as much as possible, and see if this actually holds across more systems, and try to actually collaborate with experimental collaborators to see if this how much mileage we can get out of this as well. And yeah, so the full paper is here. the title of the paper is the same as the title of the talk, and I'm assuming the slides will be shared. And the code is also going to be very soon coming as well. So yeah, I'd be happy to stick around and answer any more questions. So I guess I see another one here. Is there a reason that prompted you to use different model architectures for different systems? And would you mind commenting on the generalization capability for these trained NNIPs to different systems? Yeah, so I think we chose model architectures essentially we chose the ones that became unstable on certain systems. So some model architectures, like really good models on really simple systems, are like gonna do really well. Like for example, the NNIP model on like MD17, which is a pretty easy benchmark, at least it's considered easy these days. It never really became unstable, so we didn't really see anything interesting there. So we chose combinations of models and systems that led to interesting instability behavior. And then the generalization capability to different systems. In this work, that's a really good question. We didn't test how we generalized to completely different systems. We tested how we generalized to different temperatures and things like that. But generalizing to different systems is I would still say a pretty open problem in like ML force fields. I think there's now these foundation models, so-called foundation models, that are trained on lots of data and can kind of generalize to different systems. But I think generalizing to different systems is still a pretty open challenge, especially things like the Open Catalyst project. They have this out of distribution benchmark where you have to generalize to new different types of catalysts, and the numbers there are still pretty woefully low in terms of performance. So I think we have a long way to go for generalizing to different molecules and stuff. Can this be applied to coarse-grained systems as well, or will pre-computed observables diverge too far? Yeah, so I think there's nothing stopping us from applying StABLE training, the StABLE training procedure to coarse-grained systems. It just becomes a question of if your observable that you're computing is on the original fine-grained space, then yeah, you might, if you coarse-grain, you might lose too much information. But you could also compute the observable with respect to a ground truth coarse-grained simulation, in which case you're fine. So yeah, I think coarse-grained simulations are very much still fair game to apply this procedure.